In this module, we will look through some basics of MCS kinematic and microphysical structure. We'll start off from a complicated looking diagram from the 1970s, before extensive observations of MCSs had been collected. The figure is rather remarkable because its fidelity to realistic MCS structure is quite good, even though many of the features intuitively indicated here were not explicitly observed yet. Shown here is a canonical MCS with a leading line of convective echo trailed by a broad stratiform region. These generally occur when substantial deep layer vertical wind shear is present in the environment. Convective updrafts are found within the red oval, and stratiform regions are behind this convection, roughly in the blue oval. Note that the convective updrafts are not exactly co-located with the heaviest precipitation, which is located to the aft of the convection. Thus, the strongest radar echoes are not exactly co-located with where the strong upward motion is, which explains some of the discrepancy between idealized and modeled profiles of vertical motion and latent heating and convective elements seen in the previous module. Such mesoscale systems often have a prominent overturning circulation in the stratiform region. Aloft, a front-to-rear ascending outflow is present, and below the 0° sea level, a descending rear-to-front inflow occurs, transporting low θe air from aloft down toward the surface in the stratiform regions. The descent is accompanied by adiabatic warming and diabatic cooling driven by evaporation of raindrops. The top figure from a later paper is based on observations of canonical MCSs and shows the same salient features as that predicted prior. The shaded regions indicate where enhanced radar echoes are found, in the convective region and along the radar bright band in the stratiform precipitation. More recent updates of this figure, like in bottom left, show the anvil cloud height sloping downward with distance from the convective cores in the trailing anvil, like that seen here. As seen previously, separating the deep convection from stratiform is difficult with visible imagery alone, but the coldest cloud tops can be easily detected using infrared brightness temperatures. However, the structure of clouds beneath the cloud top is still invisible without passive or active microwave instruments. For example, radar can detect the size of the largest drops present in convection. Larger drops typically indicate the presence of stronger updrafts. Shown here are examples of two MCSs. On the left is a broad stratiform region with embedded convection scattered within it. On the right is an example of an MCS with a leading convective line moving toward the southwest. The case on the right occurs in an environment with stronger vertical shear, and winds aloft in this example were likely southwesterly. Unlike satellite imagery, radar can only see precipitating regions, and without cloud radar, the non-precipitating anvil clouds are not fully, if at all, detected. A combined analysis of radar and satellite imagery is best used to characterize MCS structure, which can vary substantially as seen in these two panels. Convection can take on a variety of organizational patterns, which is what the current figure expresses based on observations of mid-latitude continental MCSs. The canonical MCS that many schematics are based off of is that with a leading convective line and trailing stratiform, which is denoted on this figure as TS, and an example of which is shown in this pathway here, top left. However, depending on the wind profile, stratiform can be seen parallel to the convective line or even ahead of it. In the tropics, it is especially common to observe MCSs that take on no obvious structure. In other words, the convection appears to be randomly distributed within stratiform. This happens frequently in low shear environments, which are common in the tropics. The particle fountain conceptual model, shown here, visualizes how many convective cells distribute hydrometeors locally within a cloud and moisture to upper parts of an MCS, resupplying the upper level stratiform and anvil cloud with the moisture to persist. Such an MCS decays when the atmosphere becomes too stable for deep convection to develop. Indications of atmospheric stabilization would be warming of the middle to upper troposphere and cooling of the lower troposphere. For the canonical leading line trailing stratiform type of MCS, observations have shown that the rearward ascending outflow and the descending inflow mentioned earlier, the descending inflow sometimes drives formation of a cold pool in the boundary layer, which is a density current that we will describe more in another module. Conservation of vorticity drives these major flows in the stratiform region. We can show this by starting with the vorticity equation for two-dimensional flow, shown here. Theta star, in this case, represents a perturbation from an environmental mean. Given the small spatial scale, we can neglect the Coriolis effect. We can define a stream function such that its vertical derivative is the zonal wind and negative the zonal derivative is the vertical velocity. If we assume a steady state, meaning the Eulerian derivative is 0, and we define the relative vorticity as du dy minus dv dx, then we can plug the stream function in place of the relative vorticity, and the resulting equation, down here at bottom, tells us that the stream function, which is included in these two terms here, is governed by the large-scale environmental flow and the horizontal distribution of buoyancy in this third term. Streamlines of storm relative inflow are shown here for this canonical MCS leading convective line type of system. Vorticity is conserved following the streamlines in a sheared, conditionally unstable environment. And this an example of a shear profile in the zonal wind is shown at right. Three types of circulations follow from conservation of vorticity: a jump updraft, which ascends from lower right to upper left, and an overturning updraft, which sometimes breaks off from the jump updraft, and finally an overturning downdraft, which feeds into a low-level cold pool. The updraft corresponds roughly with the convective region and the front-to-rear ascending region, while the overturning downdraft corresponds with the descending rear-to-front inflow jet. We can manipulate the vertical momentum equation also while neglecting Coriolis and friction. I won't take you through the whole derivation here, but you end up with the Bernoulli equation in Boussinesq flow. If you move this buoyancy term, or this integral here, to the right-hand side, what the equation tells you is that along a streamline, the cape release can be converted not only to vertical motions like we've thought of before in prior modules, but also to horizontal motions, which is what this u squared represents, and the enthalpy of the fluid, denoted by P naught or P star over P naught. As a result, the buoyantly driven motions are not just concentrated within the updrafts in an MCS, but they're distributed throughout the system. The microphysical structure of MCSs can also be examined in the context of the flow within a canonical MCS. Shown here is the microphysical makeup of the convective regions of MCSs with the jump updraft and overturning updrafts shown by black arrows. The heaviest rain occurs within the jump updraft and is flanked by regions of moderate or light rain. A small area of rimed ice, shown in yellow, rimed ice aggregates, and graupel, can be found above the 0 sea level near the jump updraft. A region of melting wet ice aggregates are presented as the beginning of a bright band region rearward of the jump updraft. In the stratiform region, the ascending front to rear flow is seen aloft, with the overturning downdraft seen below. Part of the descending downdraft breaks off sometimes into a cold pool that promotes convergence beneath or near the base of the jump updraft, reinforcing upward motion. Broad regions of light rain are topped by wet melting aggregates. Occasional convection will promote the growth of some larger rimed particles, here in yellow. And in the upper levels of both convective and stratiform precipitation, dry, non-melting ice particles are present. And particularly in stratiform regions, small ice crystals are present. These ice crystals slowly fall through sedimentation and are often left behind as remnants of anvil cloud after the precipitating portions of the MCS dissipate.